How you doing, everybody? This is Mr. Kolakowski. I hope you're doing well. This is a video that is going to go over a quiz that you took and hopefully gives you some opportunity to review. And if you have any questions, that's going to be normal and expected. Don't hesitate to email me if something that I'm about to review is still fuzzy. Let's go ahead and jump right in. This is a table quiz that you took and a group quiz. The name of the quiz was Electric Potential, Voltage, and Electrical Potential Energy. Let's take a look at the equations here very quickly. Here we have all of these equations should look familiar. Here we have a list of equations void of positive, negative signs. The reason for that is because you can deduce from the context of the scenario whether a voltage is increasing or decreasing. Same thing with an energy state. Um, the next set of equations we have here are all capacitor specific, only for capacitors. Do not use, as tempting as it may be, uh, 1/2 QV for anything other than a capacitor. We also have some constants here. You do not ever have to memorize the mass of a proton or the Coulomb's constant or something like this. Those are things that are provided to you in the class. Okay, starting with number one, for an electron moving in the opposite direction as the electric field. Let's take a look at the picture over here on the right. The electron starts here towards the top of this negative plate in the capacitor, so towards the top of the picture, and it goes from here to here. In this particular case, an electron is going to increase its electric potential. It's moving towards the positive charge, and at the same time, opposites attract, so a negative charge moving towards a positive plate is going to reduce its energy state. So we would describe this as an energy decrease. For a positive particle, like a proton here, for number two, it says a proton is moving in the same direction as the electric field. We would say its energy state decreases, opposites attract. A proton that has moved closer to a negative charge will have a lower energy state, just like a bowling ball that is brought closer to the ground has a decrease in its gravitational potential energy state. However, because this particle is moving away from the positive charge, it will decrease its electric potential, aka voltage, and the correct answer, as you can see, is D. Number three poses an interesting situation because they tell you you have an electric field. A uniform electric field is what you get in between the plates of a capacitor. A uniform electric field of 500 newtons per coulomb strength is directed in the negative y direction. Here you can see these arrows representing the electric field point in the negative y direction. A positive 4 nanocoulomb charge moves 20 centimeters in the positive x direction. So it's a lateral move. What is the change in its energy state? Well, if its electric potential doesn't change, its electrical potential energy wouldn't change. It ends up being zero. You can think of it as, I don't know, a bowling ball that you carry across the room, but do not change its elevation, will not increase or decrease its gravitational energy, potential energy state. So that's what's happening here with number three. I think this is a strong evidence for the value of making a picture. I think I would advise for every problem in this unit, if you're having a difficult time visualizing the scenario, I do, in many of these cases. I think a picture is necessary, and here you can see it's a lateral move. There will be no change in voltage or electrical potential energy. That's not the case for number four. Number four says a uniform electric field of 250 newtons per coulomb is directed in the positive x direction. So here in this picture, you can see electric field lines pointing to the right. Positive 12 microcoulombs moves from the origin to the point x equals 20 centimeters. So in other words, it's moving in the positive x direction. What is the change in its potential energy? What is the potential difference? under which it moves. All right, so here's my picture. You can see the positive particle is moving from left to right. These are the details that have been provided to us. And the equation that fits best is QED. Plus or minus sign is here because you really don't need to get bogged down in the confusion. Is this displacement positive or negative? In this case, it's a positive displacement because you're going with the electric field. But all of these difficult decisions aside, charge could be positive or negative. Um, Electric field in this particular case is to the right. I guess that's a positive in this context. And we have a displacement that's positive just because, again, the particle is moving with the electric field. We end up getting negative QED would be negative 6 times 10 to the negative 4 joules. If you just think about it conceptually, though, positive particle moving towards this negative charge on the capacitor here in this uniform electric field, it's going to decrease its energy, just like a bowling ball that's brought from your chest to your toes is going to decrease its gravitational potential energy state. So that's where the minus sign comes from for number 4A. In order to solve for the voltage potential difference that the particle undergoes here, the change that it undergoes, you can use this equation, which is the definition of electric potential, by the way, energy per unit charge. You can actually understand the negative sign aspect just by understanding this particle is moving away from the positive charge. If you plug into EPE over Q, you get negative 50 volts. Number 5, to recharge a 12-volt battery, a battery charger must move 3.6 times 10 to the 5th coulombs of charge from the negative to the positive terminal of the battery. How much work is done by this battery? So here's the picture. Let me see if I can explain what's going on here. This here is more of a capacitor, but you can imagine a battery would do the same thing as a capacitor. Here we have a positive and negative terminal on this battery. The electric field created by the battery is going to point away from the positive towards the negative charge. And as these charges are effectively pushed by this potential difference, that's going to be an energy change. That's going to be work done by the battery. Work and energy are two sides of the same coin. So here if we take Q times V, we find out we get about 4.3 times 10 to the 6 joules of work. The reason there's a negative sign here is because let's say you use a bowling ball analogy for a moment. If an object changes its energy state, it must have been worked on. And if an object is worked on, it will change its energy state. In this particular case, the work is being done by the battery, by the electric field of the battery. And the change in energy being a certain magnitude is going to be equivalent to the work that's done of that same certain magnitude. As far as whether the work is positive or negative, well, that gets back into things we've talked about in the past. If that isn't making sense, you can consider that bowling ball analogy from that PowerPoint lesson we had towards the very beginning of this unit. Please review that, and if you're still kind of fuzzy on these details, don't hesitate to email me a question or two. For number 6, winding down here towards the end of the quiz, we have an electron released from rest in a uniform electric field. I've made a list of knowns and unknowns. I would advise that you guys do the same thing on any of the problems that you have coming up in the future. I would also advise a simple picture. Here you can see this negative electron, negatively charged electron, as all electrons are, is going to move from the right-hand side of this picture towards the left-hand side. Opposites attract. So this negative particle, this negative electron is going to move in this context, in this picture, from right to left. So to find the potential difference, we can take the strength of the electric field multiplied by the displacement. You can really understand why this is a positive sign from just the picture. This particle is moving towards the positive charge. ED gives us, with a conversion from centimeters to meters, 59 volts. Energy is a different idea measured in joules, related to voltage, but they are not synonyms. So you can actually see the equation QED that was used earlier in this quiz, giving us an energy decrease Again, opposites attract. This negative particle is going to lose electrical potential energy as it moves from the right to the left in this picture. You get 9.44 times 10 to the negative 18 joules. For part C, if you want to save a little bit of time, you can convert that energy into electrical potential energy into the kinetic energy state. So you could set electrical potential energy equal to kinetic energy, solving for the velocity of the electron after that energy conversion has taken place. But a more popular choice that people selected was to use force. The force from the electric field here is, you can use QE to get 9.44 times 10 to the negative 16 newtons. That then can be applied into Newton's second law to solve for the acceleration of this electron. You'll notice that this is the mass of an electron, much less than the mass of a proton. And from there, knowing that this particle is undergoing acceleration, you can use one of the big four kinematics to solve for final velocity. Number 7, sorry. Number 7 is the last question of this quiz. If you have a 280 microfarad capacitor with a 56 microcoulomb of charge storage in there, what potential difference should you apply to it? Okay, so in other words, this is a capacitor question. Let me go back up here to the top of the quiz. These equations here, here, and here are capacitor specific only for capacitors. For this particular problem, they give us the capacitance of the capacitor. They give us the charge that is stored up on one of the plates. So we can find the electric potential between the two plates. So you solve for voltage here. You take the 56 times 10 to the negative 3 coulombs. You'll notice this is a conversion into the standard coulomb. Here, we're converting microfarads to standard farads. You end up getting an electric potential difference of 200 volts across the plates of the capacitor. I hope you guys are doing well. Let me know if you have any questions. More videos will come, and I hope this is going to be a useful resource for some of you guys. And again, I'd encourage you to ask questions if you're still confused about some of these concepts. All right, stay healthy, stay safe. Talk to you guys soon.